Hey guys, this is going to be the final video for the PHY 113 module. Now, I like to bring up the topic of the Einstein field equations a lot because these show us that there is a very intimate connection between the shape of space-time and the stuff filling space-time. So the stuff that is in the universe ends up determining the shape of the universe, the shape of the background space-time on which all other physics takes place. Now, previously we talked about the curvature of space-time in terms of massive objects being in space-time. So the Earth is a massive object, space-time around the Earth distorts, and we interpret this distortion of the background as being gravity. But the entire universe as a whole might also possess a curvature to it. So what do we mean by something globally possessing a curvature? Think about the surface of the Earth. So the surface of the Earth is a 2D object that is curved. If we were to begin somewhere on the Earth and walk to the west and then walk west even more, we would eventually wrap around the Earth and return to our starting point. Now, if you're standing just somewhere in a big field, you do not see the curvature of the Earth, and the reason for that is the Earth is really, really big. But if you zoom out far enough, you eventually could see the Earth as being a curved object. Now, the universe we live in might behave similarly. So it's possible to show that there are three simple geometries or three simple shapes that the universe might possess. And here again, we're not talking about the curvature around an object like the Earth sitting in space-time. We're talking about the curvature of the entire universe containing all the stars, all the galaxies in existence. Now, if the universe has a positive curvature, the universe will have a finite volume. In this scenario, if you were to travel in some direction out into the universe, you would eventually return to your starting location. In a universe that has zero curvature or negative curvature, then the universe is going to be infinitely large. So if you were to begin traveling in a rocket ship in some direction, you would never return to your starting point. Now, with regard to the pictures here, the pictures above show curvature of 2D surfaces, so surfaces with two spatial dimensions. The universe we live in contains three spatial dimensions. So if I think about the sphere over here, we have a 2D surface that curves into a third dimension. These pictures are basically should be thought of as an analogy for how our universe might be. But in our case, we would have to have a three spatial dimension surface that curves around a fourth spatial dimension. And that is something we cannot visualize because we are 3D creatures living in a 3D universe, and we can't really mentally imagine what that would look like. So this picture here, I want to explicitly say, is just an analogy for how we could think about the shape of the universe. And in the case of a negatively curved universe, you would have to imagine a saddle point that exists at every location in space. Now, there are consequences of the universe having a global curvature to it. One consequence is the angles of a triangle in a flat space are 180 degrees, but in a closed or open universe, in a universe with positive or negative curvature, the angles of a triangle might be greater than or less than 180 degrees. Another consequence is that in a flat space, parallel lines will remain the same distance apart forever. But in a closed universe, which is a universe with positive curvature, two lines that are initially parallel will eventually converge and meet each other. And in an open universe or a universe with negative curvature, two lines that are initially parallel will diverge and get further and further away from each other. It's possible, in addition to these three simple geometries, that the universe possesses some other shape to it. So there do exist more exotic geometries like a 3D cosmic donut or some type of Mobius strip or other brane world models. All of these geometries have their own interesting properties. For example, a zero curvature universe of a simple geometry will be infinite in size, but if we live in a 3D cosmic donut, then we will live in a flat universe with zero curvature, but that universe will still contain a finite volume. So these are all more exotic geometries that might be possible, but what we're going to mainly focus on are the three simple geometries that our universe might possess. Also, I'll point out, if you were ever hoping to hear the phrase 3D cosmic donut in an absolutely serious academic manner, here you go. So, we have the Einstein field equations, and the curvature of the universe depends on the stuff in the universe. This is true for both local curvature, like the distortion of space-time due to a massive object that we interpret as gravity. This is also going to be true for the entire universe as a whole, and I think of this as local curvature and global curvature. But regardless, in both cases, the shape of the space-time depends on the stuff in space-time. So the matter content of the universe as a whole will determine the geometry of the universe in which we live. If we have too much matter, we will have a positively curved universe and we live in a closed universe. If we have too little matter, we will have a negative curvature and we will live in an open universe. And if we have just the right amount, then we live in a flat universe with zero curvature. So how could we go about testing what is the shape of the universe in which we live? Well, one thing we could do is we could measure the amount of stuff in the universe, because the stuff in the universe determines the shape of the universe. But this brings up a problem. How could we measure the amount of stuff in the universe when we can't see that stuff, like dark matter and dark energy? Well, remember, one consequence of a universe possessing curvature is that the angles of a triangle might add up to 180, or they might not, depending on the shape of the universe in which we live. So one thing we could do is we could use galaxy surveys. If we measure and count the number of galaxies out to a certain distance away from us, we expect that if we were to look out in a certain direction on the sky, we could count all the galaxies out to a certain distance. A flat universe would predict some amount of galaxies, but a positively curved universe, we would expect to count fewer galaxies out to that distance. And in a negatively curved universe, we would count a lot more galaxies if we measure out to a certain distance. So the number of galaxies you count will be affected by the curvature of the universe as a whole. Another thing we could do is we could look at the size of spots on the cosmic microwave background. So different geometries predict different size CMB spots. A flat universe predicts CMB spots should be of a certain size, but if the universe is closed, then these hot and cold spots will appear larger, and if the universe is open, these hot and cold spots will appear a bit smaller. So, the fate of the universe, as I said, is going to determine our destiny. The stuff filling the universe affects the geometry of the universe, and if the universe is positively curved, it will eventually collapse back on itself. And after it collapses back on itself, it will expand again. It will go through another Big Bang and then collapse on itself again and go through another Big Bang. This cycle of Big Bang, expansion, collapse, big crunch, Big Bang again, over and over is known as a bouncing universe. If the universe is flat or negatively curved, it had a Big Bang in the past, and then the universe is going to continue to expand forever, albeit at different rates. So what type of universe do we live in? What is our destiny? Well, often the curvature of the universe is parameterized by a term omega. Formally, omega is the ratio of the density of the stuff in our universe related to some critical density that would make the universe perfectly flat. So if the universe is flat, we expect omega to be equal to 1 exactly. If the universe is a little bit bigger or bigger than omega, then we live in a closed universe. If the universe is less than omega, we live in an open universe. And if we consider the three possibilities of a closed, flat, and open universe. We could look at some actual data from the CMB sky that we see. So this picture above is from the boomerang experiment. Since then, there have been more higher precision experiments, especially the Planck satellite. And what we find is we live in a flat universe. So both an open and a closed universe are still within the margin of error, but the best fit seems to be that we live in a flat universe. So based on the best available data, it looks like we live in a flat universe and our universe is going to continue to expand forever. So to finish off this course, we're going to go back to what we said the Big Bang was. So we said there was once a time in the past when the distance between every location in the universe was 0. And this is what we refer to as the Big Bang. Is this what really happened in the distant past? The answer to that question is maybe. It's not really clear. If we were to write a full and complete analysis of the history of the universe, we would necessarily need to take into account quantum effects, effects from quantum physics. These quantum effects would become important when the universe was really small. The Einstein equations that describe the expansion of the universe do not take into account quantum effects. We do know that the universe was once much smaller than it is today. The separation between locations in space used to be much less. The prediction of an early hot universe that's really dense, really energetic, does very well match with what we observe, and we could see effects of that when we look out into space. So we think we have a very good understanding of what the universe was like about 10 to the negative 10 seconds after the separation of every location in the universe would have been 0. But was the separation between every location in the universe actually 0 exactly? Well, that's not clear. There is other stuff in the universe we don't understand. We don't really know what is dark energy. We don't really know what is dark matter. There may have been other important effects in the universe that we aren't even aware of yet. And so the universe itself might be infinitely old. There might be some important properties of quantum physics that will affect the way in which space-time behaves that we don't really know about yet. There might have been an epoch when the concept of time had no meaning at all. There are some motivated pictures of how space-time might behave before the universe actually achieved 0 size and infinite energy density. But for now, all of these are just speculative, and there's no one model that is widely accepted. So we don't know how old the universe really is. We know that about 13.8 billion years ago, the distance between every location in the universe was approximately 0. This is what we refer to as the Big Bang. But the universe might have some surprises in store for us. So that is the end of these lectures, and so science marches on. And thank you. I hope you enjoyed PHY 113, and I will see you again in PHY 114.